Okay, then moving on to the design of tall vessels. First of all, the need. Why should we design a tall vessel? What is the requirement? So that is explained with the help of this diagram. So if you have a very large vessel or a very tall vessel, it must be supported on either sides by support rings or guide ropes. So these are called as guide ropes. So what is the disadvantage of that? Lot of space is covered. As the length increases, you have to provide multiple areas of support. So what is happening is the space occupied by such a very tall vessel is very large. So for a chemical industry, it is not very useful to utilize much space. So what we have to do is we have to design vessels which can stand on its own, or they are called as self-supported vessels. Okay, so that is the idea, or that is the need for design of a tall vessel. Vessels which can support itself without the help of guide ropes or guide. These are guide ropes, so they can save more area, or you can pack much things into a chemical industry. So that is the advantage, or that is the need of a design of tall vessel. Then stress analysis for tall vertical vessels. So there are two types of stress which any vertical vessel will be having. One is the stress due to the internal pressure. So inside the, where I mentioned a pressure vessel, so the whatever fluid is it containing, it will be under pressure. So that fluid will exert a pressure on the walls of the vessel. That is called as the stress due to internal pressure, and it is either tensile. It can be either tensile or compressive in nature. Tensile is elongating force. If you are pulling something by the ends, then the resulting stress is the tensile stress, and the opposite. When you are pushing something or compressing something, you will be having the compressive stress. The second one is only due to the compressive action. So in the first case, stress due to internal pressure, it can be either the circumferential stress, radial stress, or axial stress. So all these are the kinds of internal pressure which a vessel can have. Circumferential stress acting along the circumference of the vessel, radial stress along the radial direction, axial stress along the axis of rotation. So that these are the different kinds of pressure. Then in compressive, you have dead load. So dead load include the weight of the shell, insulation, heads, attachments, and the contents. The vessel will be having something inside, so that is called as the content. So all these things contribute to the dead load, and this dead load, it will have a compressive action on the vessel. The second one is the live load, so which includes the furnishing. So whatever equipment you design will be housed in a building or a structure. So what is the weight of that structure, etc., is the live load. Then the people, the plant officers which are inspecting that, and other equipment which are required. That is the live load. And for our design, we don't consider live load; we just consider dead load. Then we have the wind load. So wind load, it is causing a bending moment, or you can call it as a cantilever effect. So cantilever, it is a, you can consider it as a road which is fixed at one end, and one end is free for deflection. So if you are deflecting one of the ends, it can move in either one of the direction. So the same way is a very tall vessel. It is fixed at the bottom, and the top end is free to move. So it is equivalent to a cantilever beam. So when wind is blowing, so the wind can sway the tall object, the tall vessel in the direction of wind. So that is called as a wind load. Then you have eccentric and irregular load. So it is due to the torque of pipe, platform, ladder, etc. So if you have observed a tall vessel, it will always have some associated piping with it, or some ladders. So if the personnel have to climb to the top and verify everything is okay, there must be ladders provided. So these things will add an extra weight. They are called as the eccentric weights. Then finally is the seismic forces. So in India, we have earthquakes, but some may be very high in the Richter scale, some may be low. But whatever is the scale, we have to account for the seismic forces, so which accounts for vibration. So this is the typical picture of a tall vessel. So as I mentioned, this is a ladder. So it is an eccentric. So apart from the basic structure of the tall vessel, there are ladders, then platforms, etc. in between. So these are openings for pipelines. So pipelines may be there in between. So all these are called as the eccentric loads. So this is the schematic of what we'll be going to design. So this is our column under consideration. The total height is capital H from the top of the column till the ground or till where the support is stopping. That I'm calling as capital H or the total height. And this is the skirt height or this is the height of the support. Then this is the X I mentioned. So X is measured from the top of the column. So from the top of the column till a particular location, somewhere in between, it need not be the center. It can be below the center or above the center. This is just representation. So from the top of the column to any point in the column, I'm calling that height or that height till that part as X. And I'm calling that as the upwind side. And whatever is below that, I'm calling it as the downwind side. So we'll be performing stress analysis on the upwind side as well as on the downwind side. Stress is force by area. So all equations will be in that form. So the units will be in kilogram force per millimeter square. So the first one and the notation of stress is sigma. So sigma A. So AP, I am assuming the axial pressure along. So as I mentioned, internal pressure of three components: circumferential, axial, and radial. So since the vessel is a vertical column, we are assuming that axial pressure is only the important or the relevant one. And axial pressure sigma AP is P di divided by 4T. And the term sigma AP is the axial stress, force per unit area. P is the design pressure. Di internal diameter of the shell. T is the thickness. Okay. And to determine T, we have to use the IS code 2825. So as per the IS code, this equation is there in equation 3.1 in page 13 of IS 2825. P di divided by 200 Fj minus P. So F is the allowable stress that I have already explained in the terminology, the maximum stress which the material can withstand at a particular temperature. It is available in appendix 2825. Then J is the weld efficiency factor. So that is also available in the IS code. Then P is the design pressure. So when you substitute it, you will be getting the values. Then the next part is due to the dead weight or the compressive forces we are analyzing. And dead weight, as I mentioned, there are weight of the shell, insulation, attachments, etc. So these all are considered under the dead weight of the shell. So first thing is due to the weight of the shell. The shell itself will have a weight because of the material of construction. So sigma is weight of the shell divided by cross-sectional area of the shell. So sigma, as I mentioned, is stress is simply force divided by area. Weight here, it means the force applied in kilogram force per the unit cross-sectional area. So weight is density into cross-sectional area into height or the thickness, rho into V. So sigma shell, you will be getting pi by 4 dO square minus dA square. When you substitute the terms, you will be getting sigma shell is rho shell, the density of the shell material into X. X is the height which I mentioned from the top of the column till the point where we are considering at the upwind side. That height is X. That is sigma shell is rho shell into X. Then next is the due to insulation. So all pressure vessels, there might be temperature changes inside. So in order to limit the temperature change, we have to use insulation. So that insulation will have an added weight. So that is sigma insulation is weight of insulation into cross-sectional area of insulation, the same thing. So when you substitute everything, you'll be getting sigma insulation is D insulation into T insulation into rho insulation into capital X. X is the height till the upwind side, dm into T. Now, what is dm and what is T insulation? So dm is the average diameter of the vessel, outside dia plus inside dia by 2. Then D insulation is the outside diameter plus 2 times the insulation thickness. So that you can simply understand, if you cut open a cylinder, so there will be two thicknesses on either side. So that is by the 2 into the T insulation, and DO because we are adding insulation on the outer surface of the vessel. That is why we are considering DO here, the outside diameter. Then the next one is due to liquid and trace. So any pressure vessel, it will have a liquid inside which will be under pressure. And if it is it can be a distillation column, it may be an absorption column, it may be a stripping column, whatever it is, there may be some content inside. Some columns are packed columns, some may be tray columns. So if it is a tray column, what is the procedure is described here. So sigma of the liquid, stress due to the liquid inside, is weight of the liquid divided by pi dm into T, and weight of the liquid is number of tray into weight of the liquid per tray into pi di square by 4, the cross sectional area. Then number of trays, this is a specific case I'm discussing. X is the height till which we are considering, minus the top space. Top space meaning the when we consider the total height of a vessel, capital H, the height of the head is also included in that. Okay, so we don't usually keep trays in the head till a particular height only we keep the trays. That is why that top space is subtracted here, divided by tray spacing. Tray spacing, the distance between the vertical distance between trays is called as the tray spacing, plus 1. Then next is due to attachments, internal fittings, top heads, platform, ladders, etc. I have showed one image where you have seen the ladder, platform, etc. So weight of all attachments divided by the cross-sectional area pi dm into T. That is sigma ATT, meaning attachments. Now the total stress due to dead weight is the sum of all this: sigma shell plus sigma insulation, sigma liquid plus sigma ATT. So whatever is the sum of the dead weight, it is added up. Then next part is due to the wind. So wind, the stress due to wind can be either tensile and compressive. That is why I've written T and C. It can either cause a compressive stress or it can be a tensile one. So wind design, the stress is bending moment divided by section modulus, MW divided by Z. A section modulus you must have studied in engineering mechanics. You can what is the net area in which the stress is acting is given by the section modulus. Then for cylindrical vessels, this is the equation. We'll be designing only cylindrical pressure vessels. So you can simply note down this equation. Set is I is the moment of inertia divided by Y max. The equation for I, the equation for Y max, dm divided by 2. So you can derive this, but we don't need that. So you can simply note down the equations. Then if you substitute everything, you'll be getting Z is equal to pi d square m into T divided by 4. Then MW, the bending moment, is wind load into X divided by 2. So wind load is the load which the wind exerts on the pressure vessel. So this is defined by K1, K2, PW into X into D naught. So all this data, it is available in another IS code which we are not using. It is used by civil engineering students, so we cannot use that. So K1, it is a constant which depends on the shape factor. It is 1.4 for plates and 0.7 for cylindrical surfaces. So for we are using cylindrical surface, so the value will be 0.7. Then the next one, K2, it is the wind coefficient which depends on the period of vibration. So the motion of wind can cause a very small vibration for the pressure vessel. So that is being notated with capital T. So K2 will have the value 1 if the period is less than 0.5, and it will have a value of 2 if it is greater than 0.5. Then time period is given by this equation 2 pi by 3 WH. The terms in this equation are explained. H is the total height including support. E is the modulus of elasticity, and that is usually a constant for a material. So for our case, it is steel. We are taking it as 2 into 10 raised to 10. W is the total weight. I is the moment of inertia. G acceleration due to gravity.
Now the next part is the stress due to seismic load, and this is taken into consideration only when the tall vessels are to be erected in the particularly seismic zone. Seismic zone. If there is no prevailing condition of the seismic or the earthquake probability, there is no need to consider the seismic load. We should consider only wind load, and the wind load and the seismic load are not considered simultaneously. The seismic load is assumed to be distributed in a triangular fashion as shown in the figure, because due to this seismic load, the tall vessel is subjected to the vibration, and the minimum, which vibrations are minimum at the base of the column and maximum at the top of the column. It is the produces the horizontal shear in the self-supported tall vertical vessels, and it is again that vibrations due to the seismic load will cause the bending moment, which is maximum at the point of the junction at the bottom of the column. and it is determined by the equation given. This is empirical relations given.
Then eccentric load, I mentioned there may be some eccentric loads like pipelines or ladders, platforms, etc. So due to the eccentric load, the moment is given by this equation, sigma me divided by z. Me is the moment due to eccentric loads. W1 is the weight of the eccentric load. E1 is called as the eccentricity factor. So that also should be given. So W1, E1 plus W2, E2, etc. till whatever is the given. So now we have all these stresses, the compressive as well as tensile stresses, everything we have. Now we have to equate these stresses and solve for x. That is our objective. And we are equating these stresses for the upwind side as well as the downwind side separately. Now in the upwind side, we assume all stresses to be tensile or it leads in elongation of the vessel. Okay. So the sigma max tensile, the maximum tensile strength is sigma wind or sigma seismic, whichever is larger at capital H. So either one can be used, plus sigma AP minus sigma AP is the axial pressure, D is due to the dead weight. Now what we do is for finding sigma wind and sigma seismic, we substitute the capital X as the H value and find out at H which is the largest sigma, and we use that sigma here. Okay, so substitute X as H, then and this LHS sigma max tensile, as per IS code it should be greater than or equal to Fj. F is the tensile, the maximum stress allowable, and J is the weld efficiency factor. So LHS is known, RHS you have one variable X, you can solve for X.